So in our lottery example with expectation, we already started touching upon that question of what happens when you have an experiment which is repeated multiple times. So rather than just throwing coin once or buying lottery ticket once, you might be wondering how you estimate probabilities if somebody were to buy many lottery tickets or throw coins over and over again. This scenario where you have an experiment as before, but now rather than doing it once, you repeat it multiple times and supposedly independently, is called a Bernoulli trial. So if you, in a Bernoulli trial, the sample space now becomes all possible n tuples of elements or all possible strings over 0, 1, success failed. Because you could have, say, 5 coin tosses. The first one came tail, head, second one tail, third one tail, fourth one heads, and the last one tail. So in this case, you could represent it, if you think of heads as 1 and tail as 0, you could represent it as a string 1, 0, 0, 1, 0. And the string would be coding one possible outcome of a Bernoulli trial. So a very natural question in this situation, when you do independently an experiment multiple times, how can you estimate probability of different possible sequences from the probability of individual, say, coin toss or individual experiment being success or failure? So in order to do that, we will go back to combinatorics again. And remember that the number of strings with k ones is n choose k. That's exactly the same reasoning as we used over and over in our dividers examples. How many places are there to put ones? How many places are there to put s's in the SOUs, and so on and so forth. So probability of getting a 1 in any given trial is p. The p is kind of the main parameter. And of getting a 0 is 1 minus p. So now the probability of getting exactly k successes out of n trials is the number of all possible strings with exactly k ones, which is n choose k, times probability of getting 1 that many times, p to the k, times the probability of getting a 0 all the rest of the times, 1 minus p to n minus k. And this is where you get the formula for what is the probability of getting exactly k successes out of n trials. N choose k times p to the k times 1 minus p to n minus k. So another thing you may ask is, what is the probability of getting the very first success on the case trial? So no successes before that and success on the case trial. Well, success on the case trial you could get with probability p, and no successes in all the trials before that you get with probability 1 minus p to k minus 1. So those formulas, by the way, if you're wondering where those p to the k, 1 minus p to n minus k come from, are just coming from the product rule, because all the trials are independent. So you only need to say what is the probability of getting a 0 on the first trial? Well, that's 1 minus p. And on the second trial, that's another 1 minus p. So probability getting a 0 on both first and second trial is 1 minus p squared. What is the probability of also getting a 1 on the third trial? Well, that's p. So probability getting 0, 0, 1 is 1 minus p times 1 minus p times p, which gives us exactly those formulas. So now you may be wondering, how many trials do we need on average, again on average, going back to our expectations, to get a success? So suppose you have a friend who wants to be buying lottery ticket until he wins. Let's say the probability of winning is P, not to deal with those large numbers. So on average, how many tickets would you expect that he needs to buy before he wins the jackpot? So let X be a random variable for how many tickets he has to buy. So the probability of winning on the very first ticket he buys is P. Probability of winning on the second ticket is 1 minus P times P. Probability of winning on the third ticket, 1 minus P times 1 minus P times P. And in general, the probability of winning on exactly ticket number I, well, hopefully he will stop buying tickets after he gets the $1 million, is P times 1 minus P to I minus 1. So now, okay, let me not go into the calculation of that. You could look it up in the book, but you could estimate that expected number of how should I say, the expectation of the random variable x, the average of the random variable x, will be 1 minus p. This is what so if the probability of winning is p, so for example, winning in a lotto is 1 over 14 million, he would need to buy 14 million tickets to break even. So for a simpler example, think about tossing a coin. How many times would, on average, would you need to toss a fair coin before you see heads? Well, probability of seeing heads on one coin toss is 1/2. And by this formula, we get that on average, we expect to see heads if we throw the coin twice independently. So another place where this comes up is questions like how much time and expectation would pass before something happens. For example, somebody tells you, my system is nearly bug-free. It only has 1% probability of something going wrong in any given hour. Sounds pretty good, doesn't it? So now the question is, on average, how long will the system stay up? Well, if it has a probability 1%, 1 over 100 of hanging in any given hour, 1 over 100 will be 100. It means that on average, after 100 hours, you would expect the system to go down. 100 hours is not that much. It's a little over 4 days. So after all, having only 1% probability of hanging in any given hour is probably not going to cut it. You need something a lot smaller.